Well, hello everyone, and welcome to lecture 5 in this introduction to inorganic chemistry. A slight change in topic this week, then, as we move into a consideration of acids and bases in this section. And no course in inorganic chemistry would be complete without the consideration of certain definitions of acids and bases and some simple calculations involving pH and equilibrium constants surrounding acid-base reactions. By the end of this session, you will have an understanding of the Bronsted-Lowry acid-base theory and therefore be able to identify the Bronsted acid and the Bronsted base in common chemical reactions. You will be able to calculate acidity constants and pH. And you will also gain an understanding of the Lewis acid-base theory and be able to identify Lewis acids and bases in common chemical reactions. What I also want to do towards the end of this session is to consider the wide array of compounds that we actually define as acids and bases, because I'm sure that in your studies at school and in other introductory chemistry programs, you will have considered acids and bases. You might have looked at carboxylic acids, you might have looked at sulfuric acid, hydrofluoric acid, things which have an obvious acid or base-like identity. But of course, there are lots of other compounds out there that fall under the definition of an acid and base, but might not look like an acid or a base under initial inspection. So we classify a wide variety of species as either an acid or a base. And there are sort of two theories that we need to consider. The first was adopted by or developed by Johannes Nicolaus Bronsted, who defined an acid as a proton donor and a base as a proton acceptor. And this might be the definition of an acid and base that you are comfortable with. The second theory, developed by Gilbert N. Lewis, involves reactions that concern electron pair sharing between a donor, the base, and an acceptor, the acid. So how can we distinguish between an acid and a base? Well, many years ago, this was initially based very hazardously, of course, on taste and feel. And acids were sour and bases felt soapy. A deeper chemical understanding of acids and bases was developed by Arrhenius in the late 1800s, when he started to communicate that an acid is a compound that produces hydrogen in water. Of course, that's getting closer to our understanding of acids and bases today. So what about Bronsted acidity in this Bronsted-Lowry theory of acidity? Well, the key points from the theory are that a Bronsted acid is a proton donor and a Bronsted base is a proton acceptor. And under this theory, a proton has no separate existence in chemistry and is always associated with another species. So a good example of that is the hydronium ion. This is how we would represent, under this theory, the hydrogen ion in water as H3O+. So again, you can see that the proton doesn't have a separate existence here. It's represented by the hydronium ion. In 1923, then, Bronsted and Lowry proposed that the essential feature of a reaction involving an acid and a base is the transfer of a hydrogen ion from one species to another. And again, we often refer to the H+, the hydrogen ion, as a proton. Under this formalism then, the substance that acts as a proton donor is defined as the Bronsted acid, and any substance that accepts a proton is defined as the Bronsted base. So an example, a classic example of a Bronsted acid is hydrofluoric acid, HF. When you dissolve that in water, it donates a proton to water, and you can see the reaction there. HF plus H2O goes to H3O plus F minus, and I show you in red there the transfer of the proton from the HF molecule to water. A good example of a Bronsted base then is ammonia, NH3, which is able to accept a proton from a proton donor, in this case water, to yield NH4+. And importantly, you'll note from those two reactions that water is something we call an amphiprotic substance, that i.e. that it can act as both a Bronsted acid and a Bronsted base. And in the first reaction involving hydrofluoric acid there, it acts as a Bronsted base. It accepts a proton from hydrofluoric acid. In the second reaction that involves ammonia dissolving in water, water there acts as a Bronsted acid, where it donates a proton to ammonia. Now these are all equilibria that are established. So there is an equilibrium established between the concentrations of the acid, the Bronsted acid and the Bronsted base when you dissolve these things in water. And the attainment of that equilibrium is very rapid in water. Now, we can go a step further and start defining what we call conjugate bases and conjugate acids. So when a species donates a proton, it becomes the conjugate base. And when a species gains a proton, it becomes the conjugate acid. And indeed, conjugate acids and bases are in equilibrium in solution. So for example here, the conjugate base in the first reaction there, which is the species that has donated a proton, is F minus, and the conjugate acid, which is the species that has gained a proton in the top reaction there, is water, or H3O plus. Now, these are dynamic equilibria, so they're reversible equilibria, and the two forward and reverse reactions both depend on the initial transfer of the proton from the acid to the base. So we can write a general equilibrium, which I'll show you in the equation at the bottom there. Now it can get a bit confusing because you've got acid 1, acid 2, base 2 and base 1. On the right hand side of that equation, acid 2 is the conjugate acid of base 2. It's the species that has gained a proton. And base 1 is the conjugate base of acid 1. It's the species that is left after a proton is lost. Now I'd like you to just take 5 minutes, maybe pause the video here and look back at the previous few slides and just consider, in these fairly simple acid-base reactions, what is the Bronsted acid and what is its conjugate base? Okay, so what about the strength of a Bronsted acid then? Well, we measure the strength of a Bronsted acid by its acidity constant, and conversely, we measure the strength of a Bronsted base by its basicity constant. Let's focus on the acid, although the concepts are exactly the same for the bases. We can measure the strength of a Bronsted acid, and the example I give here is hydrofluoric acid in aqueous solution by considering its basicity constant. So all that happens when I dissolve hydrofluoric acid in water is that it donates a proton to water, and there is an equilibrium established between the reactants and the products of that acid-base reaction. And I can express that equilibrium in the form of the acidity constant. So here, the acidity constant Ka is equal to the concentrations of the products, H3O plus and F minus, divided by the concentrations of the reactants, HF. And you'll note I don't include water in this because it's the solvent and it's present in very, very large concentrations. I show you there just a generalized scheme on the far right-hand equation. And here X just denotes the molar concentration of the species in question. A value of this Ka value, which is below 1, implies that the concentration of Hx is very large with respect to X minus. What that tells us is that proton retention is favoured by the acid. So look at the value for the acidity constant for hydrofluoric acid. It's 3.5 times 10 to the minus 4. What that's telling is well below 1, and what that's telling us is that only a small fraction of HF molecules are deprotonated in water. Of course, the fraction of deprotonation of HF molecules is a measure of its strength. Now, it's quite easy to calculate the acidity constant for an acid. So let's have a look at the example here. The pH of a solution of 0.145 molar ethanoic acid here is 2.8. And we're asked to calculate the acidity constant for ethanoic acid. So the first thing we do is to write the formal equilibrium equation for the acid-base reaction. So we've got our ethanoic acid plus water going to H3O plus the ethanoic acid minus the proton. We can write an equation that describes the equilibrium constant then, which is found on the far right of the yellow box there. Ka is equal to the products divided by the reactants in terms of concentration. And you'll note that in order to calculate the acidity constant, then we need to calculate the concentration of H3O plus, the concentration of deprotonated ethanoic acid, and the concentration of ethanoic acid in this solution. And remember, this is at equilibrium. Let's start in the blue boxes then, in the far left-hand side. Perhaps the easiest thing to calculate is the concentration of H3O plus, because we've got a value for the pH, and we know that the pH is equal to minus the logarithm of the concentration of H3O plus ions, and we can rearrange that to solve for the concentration of H3O plus, which is equal to 10 to the power of minus our pH value, which is 2.8 in this case. When you calculate that, then you get a value of H3O plus for as 1.6 times 10 to the minus 3 moles per decimeter cubed. If we know the value for the concentration of H3O plus, we can easily calculate the value for the concentration of deprotonated ethanoic acid, in this case CH3COO-. So take a look at the middle blue box here. We know that each deprotonation event produces one H3O plus ion, and of course if it's produced one H3O plus ion, then we know that one ion of CH3COO minus must be produced. So those two concentrations are equal, and the value of the concentration of the deprotonated ethanoic acid is also 1.6 times 10 to the minus 3 moles per decimeter cubed. The only other value that we have to calculate is the equilibrium concentration of the ethanoic acid, which is going to be equal to the molar concentration, which is 0.145, minus the concentration of any deprotonated ethanoic acid. In this case, it's 0.0016. So the equilibrium concentration of ethanoic acid then is equal to 0.143 moles per decimeter cubed. All we have to do then is feed that into our equation that describes the acidity constant, and we get a value of 1.7 times 10 to the minus 5. Now we can also determine the strength of a Bronsted base, and we do that in exactly the same way. We write these proton transfer equilibria as basicity constants now, again with the concentration of the products divided by the concentration of the reactants. And we think about their magnitude in exactly the same way. So if that basicity constant is well below 1, then the concentration of the protonated base, if you like, the conjugate acid, is well below that of the base, and only a small fraction of our base molecules are dissociated. So therefore we know that the base is a weak proton acceptor. Now water is an interesting one because it's amphiprotic, and in fact proton transfer equilibria even exist in the absence of any added acids or bases, and this is known as autoprotolysis, and it's incredibly rapid and involves the interchange of weak hydrogen bonds between neighbouring molecules. And you can describe its extent and composition by something called the autoprotolysis constant. An important consequence of this autoprotolysis constant of water or of any solvent is that it allows the relation of the strength of a base to the strength of its conjugate acid. And this is useful because it provides a single constant which is able to express the strength of both the acid and the base. So think back to that ammonia equilibrium that we looked at a couple of slides ago, in which ammonia acts as the base. Well, that's also related to the value of the conjugate acid. And you can relate that to this autoprotolysis constant, the acidity constant multiplied by the basicity constant. What this tells you is that if you have a large value for your basicity constant, then you will have a smaller value for your acidity constant, or essentially, the stronger the base, the weaker its conjugate acid. So to put that into numbers, the basicity constant of ammonia and water is 1.8 times 10 to the minus 5. And we're able to calculate the acidity constant for its conjugate acid, which in this case is NH4+, because of this phenomenon known as autoprotolysis. So the acidity constant of the conjugate acid multiplied by the basicity constant of ammonia is equal to this Kw, this autoprotolysis constant. And by rearrangement of that equation and knowledge of the basicity constant of ammonia, it's possible to calculate the acidity constant of the conjugate acid of ammonia, which is NH4+. Now, this is essentially just another fancy way of expressing the strength of the base. Now, these acidity constants span many orders of magnitude. You'll notice in the last few slides, I've shown you some basicity constants that do span at least a few orders of magnitude. So it's far more convenient to report them as their common logarithms, or logarithms to the base 10. The pK value then is equal to the minus log of K, where K can be any of the acidity or basicity constants that we've previously discussed. And an acid or a base is classified as either weak or strong depending on the size of its acidity constant. So have a look at these values here. Look at the strong acids, such as hydrochloric acid. It has a very high acidity constant, far greater than 1, 2 times 10 to the 6. What that tells us then is that in solution, the concentration of molecular HCl is very, very low. And the overwhelming majority of HCl molecules have dissociated, or a proton has been donated to water and Cl- ions reside in solution. Its pKa value then is less than 0, minus 6.3. So if you have a pKa value which is less than 0, but a Ka value which is greater than 1, you would predict a strong acid. Compare that with hydrofluoric acid in the table there, and you can see that its Ka value is less than 1 at 3.5 times 10 to the minus 4, and its pKa value is greater than 1 at 3.46. So hydrofluoric acid is a relatively weak acid. Now, of course, some acids can donate more than one proton, and we call them polyprotic acids. A good example is hydrogen sulfide. And there are therefore 2 successive proton donations and 2 acidity constants. So I show you the first acidity constant for H2S there, followed by the second. And you'll note a very large difference in the 2 acidity constants. So the second acidity constant is almost always much smaller than the first acidity constant. And all this is, it's a very simple explanation. The second removal, or the removal of the second proton, has to be removed from a center with a negative charge. So look at the first acidity constant. H2S plus H2O goes to H3O plus HS minus. In the second acidity constant, we've got to remove a proton from a center which already has a negative charge. So it's energetically unfavorable for that to happen. It requires more energy to remove a proton from a centre with a negative charge, and therefore that proton really doesn't want to be removed from HS minus, and the second acidity constant is much lower. Now, Bronsted acid-base chemistry tends to focus on acids and bases in water. And we've only really discussed examples of acids of the type HX, HF, HCl, H2S. But the largest class of acids in water consists of species that donate a proton from an OH group attached to some kind of central atom. And a donatable proton of this kind is called an acidic proton. So let's have a look at some examples of those. The first is an aqua acid, where the acidic proton is on a water molecule that's coordinated to a central metal atom. There's a general reaction scheme shown there. The Bronsted acid then is the molecule with that acidic proton, and the conjugate base is the molecule after it's lost a proton. So here's a good example at the bottom of an iron compound which is surrounded by 6 water molecules, and each one of those water molecules has a donatable proton. And you can see that you can identify the Bronsted acid, Bronsted base, and the conjugate base and the acid. There are things called hydroxoacids and oxoacids. A hydroxoacid is where the acidic proton is on a hydroxyl group without a neighbouring oxo group. So you can see there TOH6 is a good example. And an oxoacid is where the acidic proton is on a hydroxyl group with an oxo group attached to the same atom. So sulfuric acid is a good example of an oxoacid. You can actually see all 3 of these in action if you analyse the successive stages of a D-block metal in an intermediate oxidation state, such as this ruthenium compound. Have a look and see if you can identify the sort of proton donation mechanism for each of those. What about Lewis acidity then? We've focused very heavily on the transfer of a proton between species. So that's exactly what the Bronsted-Lowry theory deals with, is the transfer of a proton from the acid to the base. But is there a wider definition of acid-base chemistry that we can use that may involve compounds that, by where the reactions don't necessarily involve the donation and the acceptance of a proton? The Lewis theory of acidity was developed by G.N. Lewis, and it's a far more all-encompassing definition of an acid and a base. And Lewis defined a Lewis acid as a substance that accepts an electron pair, and a Lewis base as a substance that donates an electron pair. And you can see there's a general reaction scheme at the bottom there that shows this. We're not talking about protons now, right? We're talking about electron pairs. Now let's go back to our example of ammonia. here, the proton acts as a Lewis acid. Because it accepts an electron pair. It's able to attach to an electron pair. It's able to accept an electron pair. It accepts an electron pair, in this case from ammonia. So any Bronsted acid then, because as it provides protons and it accepts electrons, we can say exhibits Lewis acidity, and the same is true for any Bronsted base. Any Bronsted base exhibits Lewis basicity. However, as I said, the proton isn't essential to the definition of a Lewis acid or base. And the nice thing about Lewis's theory is that it's extended over a wide range of substances. So it's a far more encompassing theory that defines whether or not something is an acid or a base. And it's entirely based on the acceptance or the donation of an electron pair. So some key points to remember then in the Lewis approach: a Lewis acid accepts electron pairs, a Lewis base donates electron pairs. The reaction between the two leads to a formation of a complex, and all Bronsted acids and bases exhibit Lewis acidity and basicity. So the Bronsted approach is still valid under the Lewis approach. In fact, the Bronsted approach is a formalism under the Lewis approach that deals with the transfer of protons. But importantly, the Lewis definition can be applied to aprotic systems. It can be applied to systems that don't involve the transfer of a proton. So let's have a look at some examples of Lewis acids and bases that don't necessarily involve the transfer of a proton. Any molecule that has an incomplete octet. So if you cast your minds right back to lecture 1 and 2, where we were looking at Lewis structures and VSEPR theory, some of those molecules that we were looking at, we can actually identify the Lewis acid and Lewis base. If a compound has an incomplete octet of valence electrons, it might wish to complete its octet by accepting an electron pair. So have a look at the reaction between trimethylborane here and ammonia. Ammonia donates an electron pair to the trimethylborane. Under the Lewis definition, the ammonia molecule here donating its electron pair would be defined as the Lewis base, and the trimethylborane molecule, which accepts an electron pair, would be defined as the Lewis acid. So you can see the final product then is an adduct or a complex, a molecule, and that reaction has involved no protons, but we can still identify an acid and a base under Lewis's scheme. You can define a Lewis acid or a base when you think about a metal cation in aqueous solution accepting an electron pair, which in this case will be the molecule that surrounds the metal cation. Have a look at the molecule at the bottom right there. It's a cobalt molecule which is surrounded by 6 water molecules, and each of those water molecules donates a lone pair to the cobalt atom in the middle. And the chemists, we will study this in a lot of detail in the second half of this module. These are called transition metal complexes. And the water molecule here then that surrounds the cobalt is the Lewis base, because it donates electron pairs into some vacant orbital that surrounds the cobalt atom. The cobalt metal then in the middle is the Lewis acid, because it's accepting an electron pair from the surrounding water molecules. Now, a molecule or an ion with a complete octet may be able to rearrange some of its valence electrons and accept an additional electron pair. So CO2 can actually act as a Lewis acid when it forms HCO3- because it accepts an electron pair from an oxygen atom in the OH- ion. And in some strange circumstances, a molecule or an ion might be able to expand its valence shell, or the radius of that ion might simply be large enough to accept another electron pair. And you can see here this SiF4 molecule is able to accept electron pairs from 2F- ions, which act as the Lewis bases, to yield SiF6. Now take a look at the two equations I show you there and attempt to identify the Lewis acid and base in each of the following reactions. Just have a think about that. Pause here and have a think about that. Now we can look at the periodic table and we can understand some of the trends in Lewis acidity as you cross the periodic table, and it allows us actually to predict a lot of the reactions that S and P block elements will undergo. So in the first two groups of the periodic table, think about what happens when you put sodium into water. Sodium reacts very vigorously and is very easily solubilized in water, and it exists as a sodium ion in water surrounded by a hydration shell in which they are accepting electron pairs, if you like, from water. Beryllium dihalides act as Lewis acids when they form these long polymeric chain structures. Group 13, so we skip the D block here and move over to the P block. Boron and aluminium trihalides have incomplete octets, and very similar to the reaction that I showed you a few slides ago, they are able to accept a lone pair from a Lewis base. And similarly, the group 14 elements can exhibit these kinds of properties. So think about that strange silicon molecule I showed you. These are able to exhibit something called hypervalence. They act as Lewis acids by expanding their valence shells and becoming 5 or 6 coordinates and accepting electron density from a halide. Tin, if we go to near to the bottom of group 14, is able to is both a Lewis acid and a base. Tin SnCl2, tin 2 chloride, will combine with a chloride ion to form tin trichloride. and that can then act as a Lewis base in metal-metal bonds with manganese. Group 15 then, the heavier elements of group 15, so antimony, bismuth, moscovium, are able to form some of the most important Lewis acids. So have a look at SBF5 here, and what happens when you react it with hydrofluoric acid. The SBF5 acts as a Lewis acid here because it accepts a pair of electrons from the fluoride ion, and the fluoride ion is obviously the Lewis base, and that produces a superacid, H2F+. Group 16 then, sulfur dioxide, is both a Lewis acid and a Lewis base. It's able to form a complex with trialkyl amines, where it acts as the Lewis acid by accepting an electron pair. But it can also act as a Lewis base. It can donate either its sulfur or oxygen lone pair to another Lewis acid. Sulfur trioxide is a strong Lewis acid, and in a very similar way to sulfur dioxide, it can react with trialkyl amines. And a classic aspect of the acidity of SO3 is its very exothermic reaction with water, where it produces sulfuric acid. In group 17, bromine and iodine molecules can act as mild Lewis acids. Okay, so some conclusions then. A Bronsted acid is a proton donor, and a Bronsted base is a proton acceptor. A Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. Importantly, these theories complement each other. They're not opposing theories. It's just the Lewis theory, that the Bronsted theory is a product of the Lewis theory that involves protons, whereas the Lewis theory is a slightly more all-encompassing theory that involves the donation of electrons and the acceptance of electrons. And the important consequence of the Lewis theory is that it allows us to consider aprotic systems. And hopefully what I've shown you is that there are a wide variety of chemical compounds that can be called acids and bases, and they don't always have to involve a proton. So I've put some tutorial questions up on the Moodle page associated with this lecture. What I'd like you to do is have a go at these questions, and I will go through them. So you can pause here, you can have a go at the questions, and I will go through them when you're ready to hit play. So question number 1 asked us to identify the conjugate base which corresponds to the following acids. So this one here, we remember that we're trying to identify the conjugate base. So this is the species that's left behind after the proton is lost. The first example is an example of an aqua acid. So the proton is lost from a water molecule, which is coordinated to a central metal ion. So you can write out the equation, and the conjugate base there is shown in red. And you'll note that all we've done is taken a proton from the water molecule that's coordinated to that central cobalt atom. I think this is quite a simple one. Clearly, if that loses a proton, it becomes CH3O minus. This is an example of an oxoacid. So here our acidic proton is on a hydroxyl group where there is an oxo group also attached to the same atom. So I circle the oxo group in red there. The conjugate base here then is very simply HPO4 2 minus. We just take a proton off of that H2PO4 minus. This is an example of a hydroxoacid. So here our acidic proton is on a hydroxyl group, but we don't have a neighbouring oxo group. And here the proton is lost from one of those hydroxyl groups. In question 2, we're asked to identify the conjugate acids for the following bases. So remembering that the conjugate acid is the species that's formed when a proton is gained. So first of all, pyridine. Pyridine is able to accept a proton in the manner shown in the red box there. And O2 minus can accept a proton. This is an interesting reaction because here OH minus is both the conjugate acid and the conjugate base. Question 3 asks us to calculate the equilibrium concentration of H3O plus in a 0.1 molar solution of butanoic acid, and it gives us the acidity constant for butanoic acid and then asks us to calculate the pH of this solution. So the first thing that I've done is to write out the equilibrium equation that represents what happens when you dissolve butanoic acid in water. Butanoic acid donates a proton and we get H3O plus ions. So I write out an equation here that describes the acidity constant, the concentrations of the products divided by the concentration of the reactants. And you'll note again, I negate H2O here. I've already got a value for my acidity constant, 1.86 times 10 to the minus 5. I've rearranged the equation there. All I've done is moved the concentration of butanoic acid to the left-hand side of the equation because we know that is equal to 0.1. And we know that the concentrations of H3O plus and CH3H7COO minus are the same because one proton donation event yields one H3O plus, so that's equal to x squared, where x is our unknown value. So the square root of 1.86 times 10 to the minus 6 here is equal to 0.0014 moles per decimeter cubed, and that gives us the concentration of H3O plus in that 0.1 molar solution of butanoic acid. To calculate the pH of the solution then is just minus the logarithm of the H3O plus concentration, and the pH of that solution is 2.9.